Okay,
so my
no problem.
apologies.
So,
It was my mistake then.
no, don't worry.
Maybe you check the share screen.
Yeah, I think it should work. Just give me a second.
Please, James, make him as presenter.
Yeah, it's
Okay,
like,
fantastic.
Can you see my screen now?
Yes, fantastic. It's perfect.
Okay. Can you still see it?
Yes.
Yeah. Because I need. Okay, let's go again. Laser pointer. Laser pointer. Okay. Okay. So more or less ready.
So you tell us, Pedro, shall we wait another 4 minutes until?
Yes, please. Yes.
Or shall we get started straight away?
No, just more 5 minutes. No, or two.
Okay.
More 5 minutes.
Is that all right with you, Pavel?
Yeah. I will just call my student because we had a meeting right now. I will tell him that I will just skip it. Okay.
Sorry about that.
Could you speak Czech, Cedric?
I can. But
you can?
I can speak Czech, but if I'm going to have a serious conversation, then I'd rather not. And when I'm at a bar and at a pub and having beer, then my Czech goes very fluent.
Thank you.
Remember, it was good. It was pretty good.
But
thank you.
When I'm fighting with my wife, then I don't speak Czech because.
Oh, okay. But is it easy or is harder than English?
No, it's easy for you to get a tongue fracture when you try to speak Czech.
But thank you.
Děkuji is formal. They usually say děkuji.
Okay, because I learned one word in Czech.
But if you want to speak, if you want to pronounce this word, I'll write it in the chat for you. Yeah, he does speak Spanish. You see the word that I sent to you in the chat?
I can.
This
how
is
can I
ice
say
cream.
this word?
This is ice cream.
Ice cream.
Pavel, I'm just teaching Pedro some Czech words. I wrote it down at the chat, and I'm challenging him to pronounce it.
You mean zmrzlina or what?
Yeah, zmrzku. Yeah, zmrzku. Zmrzku is even harder than zmrzlina. Right.
But Jelinek, you can speak a good Spanish,
Here.
no?
Yeah. We have a couple of people here who are from Spain. I spent like 6 years in Spain, and now in the group there is a good connection with Madrid. So basically, I think at the moment we have like 4 or 5 people from Spain. So seems like in group that mostly I'm speaking Spanish than Czech.
Okay. I guess we can start, no, Cedric and Jelinek.
Yeah.
Yeah. Oh, okay. James, we can go live to YouTube.
Yes, we are live.
Okay, thank you. So, thank you for watching us live on YouTube. Welcome to the Nanos Colloquium organized by the Nanoscience and Advanced Materials graduate program of the Federal University of ABC. Today, we are pleased to present Professor Pavel Jelinek of Czech Academy of Sciences. I also want to thank Professor Cedric for helping us to bring Dr. Jelinek to this seminar. Please, Cedric, could you introduce Professor Jelinek?
Yes, okay, Pedro, thank you. So it is a great pleasure for me to introduce Pavel here. I met Pavel back in 2006 in Manaus. We were going for a conference there at a beautiful hotel that nowadays is only ruins, right, Pavel?
I saw it.
And I was in my PhD, and Pavel, I think, was just returning from a period in Spain, was returning back to Prague, and where he has been since then. So I remember that I saw Pavel and his colleagues at the airport, and from the distance, I thought, these guys are Czech. And I just walked to them and I greeted them in Czech. And I remember how surprised they were hearing someone speaking Czech at the airport there. Anyway, so Pavel is a theoretical physicist. He does mostly modeling, that's his training on. And Pavel wrote a code on non-equilibrium Green's function transport, right, Pavel? Which is coupled with Fireball, which is a localized basis set code. And nowadays, Pavel is the leader of a group in Prague, in the Czech Republic, where they have a very important, they were able to build what Pedro just said is the dream of every theoretical physicist, having a strong experimental group connected with a strong theoretical group. So Pavel and his group, they have been very successful in this interaction. And they have been publishing very interesting papers in very high profile journals. And it's going to be a pleasure to see what they have been doing now. I remember when I visited Pavel's group, I'm not sure which year it was, but I was very impressed to see that they were not only buying and using experimental equipments, but they were also making their own. They had a very sophisticated MBA equipment that they used to synthesize graphene and measure interesting properties in them, right? So the last thing that I wanted to say is that when we were in Manaus, Pavel tried some very bad caipirinha, and there he learned the real meaning of the Czech word kocovina, which means a hangover. And then when I visited Prague, Pavel in Prague, I made sure that I brought him some good cachaça so that I would undo any bad image that our national drink would have in his trajectory. So Pavel, thank you very much for accepting to give us a talk. And yeah, we are all yours now.
Okay, so thank you very much for very kind words, and also for, of course, for invitation. I mean, it's of course it's pleasure to talk about the ocean without being moving out of Prague. So okay, going back to science. I mean, today I want to share with you some recent results we had about like low-dimensional, or especially one-dimensional systems, molecular systems grown on surfaces. And the aim of this, basically our effort recently, is to really look at these one-dimensional systems and try to get some exotic features like of the quantum mechanics, which is living in this one-dimensional world. So basically, let me just show you some outline of my talk. So first, what I'm going to talk about is some general introduction, why 1D, why all these things. In the second part of the talk, I would like to talk about the p-conjugation and the topology, like this, this kind of hot topic in condensed matter physics. But I want to show that actually this topological concept, or the concept of topological band structure, could be also applied for chemists. And actually there is an interesting connection between what we call these topological bands, topologically protections, and what chemists they call the p-conjugation. And finally, if there will be time, if you will not be too tired, I also would like to talk about some very interesting stuff where we start to look at this nuclear quantum effects, or proton tunneling, which may exist in these one-dimensional supramolecular chains, and it actually may modify not only like mechanical properties, but also the electronic properties itself. Okay, so let's go. So 1D systems. I mean, of course, these days everyone is talking about two-dimensional materials, and if you have to think a little bit about why two-dimensional materials are so exciting for us these days, it's because before we have been living in a bulk 3D and moving to 2D, I mean, we reduce the dimension, and this reduction of dimension introduce more correlation. So it means that the electrons, they feel each other much seriously, or any quasi-particle in 2D. Of course, this confinement creates some interesting chemical properties, and then there is a strong correlation. But if you go to 1D system, so even if we reduce even further this dimension, you will completely change the picture. I mean, what will appears is like this Tomanaga-Luttinger liquid. What you will see that actually the phase diagram of any of these materials is very complicated. There is an example here that you see that actually at the tuning some parameters, you can go to very different phases. And actually, to just get a feeling about these 1D materials, why it's so different, I mean, also you can feel it in your everyday life. You don't have to deal with the quantum mechanics. The one interesting stuff is, for example, which you can experience every day in the highways, that actually this is truly 1D system. So basically, there is no way, if there is some obstacle on your way, there is no way to go around. You have to really, and so it means that you feel every particle in the line. It's the same when you go to the post, you wait in the queue, and if someone will move in this queue, you have to move on too. Yeah. So it means that now we see that that's completely changed the perspective. So what you have is basically that the quasi-particles, they are no longer like entities. Always you talk about not single excitation, but there is a collective excitation. And that's something which is beyond this Tomanaga-Luttinger liquid. Okay. And I will show more examples on this 1D, what basically means, and the connection with this p-conjugation. Of course, so this, and there's another nice view to see consequence of this is the screening in one-dimensional. So you can do it by your hand, and you can just look at what is the response function of the electronic properties to external stimuli, and you can calculate the susceptibility. So it means how the electronic gas responding in 2D, 3D, and 1D to some external perturbation. And what you will find is actually that in 3D it's pretty okay. So there is some divergence when you do this kind of perturbation theory. But then you will start to see that actually in this limit, that this your Q, so it means this excitation with certain wave number means like double of your Fermi wavelength, then starts happen some instability. So basically on the Fermi level, you are no longer able to screen any impurity or any perturbation. So it means that the system starts to be unstable. And one of these things in one-dimensional system, in two-dimensional system, there is something in between 3D. So, but in one-dimensional system, there is a strong evidence basically which is behind all these Peierls instabilities or Chanteler instabilities, which are related to this kind of inefficiency to screen any perturbation and electronic gas on the Fermi level. So in principle, it means that one-dimensional system, they are very hard to be metallic. Okay. Now, if I want to study these one-dimensional systems, and people already did times for a long time, the question is, if you know, I mean, if you are a theoretician, that's fine, but always you would like to have something in hand which is real. And of course, there are systems like in the case of graphene, the success of 2D was that we have a graphene, now we have other materials, but I would like to have also something which would be realistic. It would not be just, you know, like some crazy theoretical thinking. So we need to have some materials which basically features these one-dimensional systems. And of course, there are systems very interesting, like even though are bulk materials, but they have very strong 1D internal order, like these organic salts And these materials also features very important or very interesting properties like high TC, charge density waves, etc. Then you can also build naturally like quantum wires in one-dimensional devices. You can also look in domain boundaries in 2D materials. These domain boundaries, basically, you can consider them as a one-dimensional system. Also very interesting are carbon nanotube and, of course, the conductive polymers. So here in this talk, I'm going to talk about the polymers, as was shown already, that I'm going to talk about the molecular systems. But there is one problem with conductive polymers so far. So this is the picture of transmission electron microscopy. And being again theoretician, I'm dreaming about to just work with just one polymer. I don't want to deal with some bulky chunk of polymers, because then it's very difficult to really go in details and understand all these interactions. Okay, because there is an interaction between different polymers. You don't know exactly what the polymers looks like, etc. So that's what we want to do and the proposal is here. So we want to really go to the atomic scale, and we want to combine, in the best way, we want to grow these organic polymers in UHV chamber under the microscopy. We want to use this scanning probe technique to characterize their chemical structure. And also, in best case, I'm not going to talk about this here, but we already on it. It's to pick up these chains or these polymers from the surface by tip and measure the transport through the polymers. So to grow on the surface, to design them on the purpose, because one of the problems when you deal with polymers is the solubility. If you create the polymers in solutions, basically you are not able to disentangle them. They are very purely, it's very difficult to make solution of these guys and work just with one polymer. So always when you measure the properties of polymers, you measure the properties of bulk polymers, and then it's not possible to just disentangle and say what is the characteristic of one polymer. But now there is a recent development of what is called on-surface chemistry, and that the idea is basically that you put the molecule on the surface in UHV chamber, and now you introduce the reaction under these conditions. And that was very nice paper of Leonard Grail and these guys, where they show that you can put the molecules under UHV, and you introduce some chemical reactions, and at the end you can grow some, let's say, either 2D or 1D molecular chains. And that's now these days, it's very active field, and there are many surprises, and it's very interesting to look at it, because actually here we can create or synthesize the things which normally in traditional organic chemistry are in solution are not available. And on top of that, of course, then we can use this also recent progress in this scanning probe technique, that these days we can see directly the chemical structure. So let's say 10 years ago, when you talk about scanning probe microscopy, it was great, you could see atom, but from perspective of chemistry, it was very difficult, because as the best images was this kind of ovaloids, what you see here. So this is either in atomic force microscopy or scanning tunneling microscopy. This is unknown molecule, so you know what you deposit, it's pentacene molecule. But this is the best image which you could get just using the standard STM technique. But the science is driven by accidents. So what happened is actually the people, they've been working with CO molecules for a while. But then in Zurich, in IBM Zurich, in one day, they just mixed two things together, like these organic molecules and the CO. And what happened, that CO just came to the tip, so it was picked up, it was on the surface, and these guys, they pick it up. So normally when you have a CO on metal, you see like two dark spots, and then sometimes when you approach the metallic tip very close, you can pick up one of the CO. And how you know this is actually that this dark CO turns to be bright. So that's a signature that actually your CO is on the surface. And with this kind of weird tip, which is not terminated by atom, but CO, which is hanging on the surface, when you approach towards the molecule, now this ovaloid really starts to the chemical structure. So with that, actually you can see individual benzene rings, okay? So that's actually these days, this technique is very popular, and you can also achieve the atomic or this submolecular resolution in STM, in non-contact AFM, and also with inelastic electron tunneling spectroscopy. So we contribute this development of this field. Not only that we shown in 2017 that actually all these three channels, they can be acquired at the same time. So this is the paper we published, where the first time we acquired at the same time all these three channels. So this proves that actually the mechanism behind reaching this submolecular resolution is the same for all these three channels. But we also developed the model, which now is commonly accepted as an explanation, what is the behind of this imaging. And it's not only the model which explains us what is there, but it's also the toolkit, simulation toolkit, which we can use and actually simulate these images. Okay, so you see this is the experimental data taken in our lab, and this is the simulation. And this is also some kind of comparison simulation and experiment for STM, AFM, and EITS. So very briefly, what is behind of this contrast? So you can see it actually here, what we call this method pro-particle method. So it means that we have a CO is kind of like particle which is hanging freely on this apex. And then when you approach close to the surface, what happens is that the CO starts to bend. And this bending somehow introduces the enhancement of the contrast. So there are two effects. The first effect, if you have a metallic tip, and you approach the molecule, typically what happens that you pick up the molecule from the surface, and that's it. But now when you decorate this tip with CO molecule, what happens is that you passivate it chemically, the tip. So the CO is not very reactive. So now you can go very close to the molecule, to repulsive regime, and you can basically now to see the bending of CO in stable condition, which is enhancing this contrast. So these days, this is kind of like technique which is spreading out around the world, exciting many chemists. And also this technique is now not only about the imaging, but it's also, we can, for example, analyzing solution data, you can get information about electrostatic potential of given molecule. We can also see different spin state, etc., etc. And there is a ongoing progress on this technique. And finally, I mentioned I'm not gonna discuss this today, but also you can just, when you grow these chains on the surface, you can pick them up from the surface, and what you can measure, and actually was done in the group of Leonard Grill, when they grow these guys, they pick them up from the surface, and you can measure the current. And these days, when you combine it with AFM and STM, you can also measure simultaneously current and mechanical response. So here, recent work which we have done growing these organometallic chains made of ferrocene, and this is kind of simulation which you see what happens, pull the system out, and this is the mechanical response which you measure. And of that, you can also measure the transport properties and so on and so on. But I'm not going to discuss this today. Okay, so now let's make a very brief introduction to the topology, and I will try to convince you that basically the language of topology, which is now very active, or maybe buzzword in condensed matter physics, could be also translated somehow to the p-conjugation or chemists. So if you look in, what does it mean, p-conjugation? Maybe you are not aware of this. And so the p-conjugation means that all these carbon-based materials, they are connected by some bonds, okay? And if it's just carbon-made, then you have 4 free electrons per atom, and these p orbitals, and you want to somehow saturate them. So it means that the system tries to develop and makes like simple double bond, triple bond. And the idea is that each carbon had like 4 connections somehow, or still like 4 4 electrons in that. And that means that, for example, if I have a carbon here, so then this carbon established single bond with this carbon and triple bond with this carbon. So it means that now he has a 4 electrons somehow saturated. But now you can, of course, there are many ways how to assemble it. So for example, one would be that I have a simple bond here, triple bond here, and simple bond here. Or other one would be that I have like double bond and double bond and double bond. So it means that this carbon has 2 bonds here and 2 bonds here, and it will be the same. But that imposes later on somehow how other bonds should be organized. Okay, so and then if you do it like this or this, it means that at the end here there will appear some free electrons. So this we will call like Kinoid structure, and this one is more like aromatic structure. Okay, so it means that also relates if the system then it's closed shell or open shell. So again, you can have a look on these polyaromatic conjugated polymers as a combination of two things. The one is of course electronic correlation, but the other one is also on top of that, because now not all the bonds are the same. It's also kind of like local distortions, and this gives rise to this kind of vibronic effect. So now what you see here in this system is very complex, that there is an interplay between the electronic correlation and also, let's say, some like vibronic correlation. So maybe it's such why such complex system. And I will talk in a minute about this Yanteler distortions or the Peierls transition. So in principle, you have to see that each carbon bond has a certain spring, you know, and now it interplays between how to minimize this deformation of these springs and satisfy the lowest correlation. So it means that at the end, if you look to these guys, each bond is not equal, okay? Each of them is a little bit different. And that also has some implication to electronic structure, as I will show in a minute. Okay, and importantly also you will see is that basically this bond length alternation is somehow responsible for opening the band gap. Okay, and that's what is known, what we know. I mean, condensed matter physicists, we know that what we call this Peierls or the dimerization case, and which comes again what I told you about the screening in one-dimensional system, that basically for metallic system, one half filled, this system always in unstable. That's what the Peierls shown. And there is a transition from metal to insulator. So you open the band gap, so partition between electronic correlation, because when you open the band gap, there, of course, then you do this dimerization. The gain in electronic structure is much higher always than this deformation energy, that you will make one bond shorter and one bond larger. Okay, and that's basically what the Peierls, and it can be generalized what we call these pseudo-Yanteler effects. And from chemical point of view, actually the chemists, they know that this kind of bond length alternation is directly related to the band gap. So if the difference in these bond lengths means shorter and longer is bigger, then you open the band gap. Okay, so there is some kind of like empirical rule. And what is also known, that this cumulin, so it means like connection double, simple, double, it's unstable due to the Peierls, and you will get a simple, triple, simple. So that's the chemical point of view. Now let's have a look what the people have been studying for 30 years already, and it actually the Nobel Prize in chemistry was for that, is what is called this SSH model, the Su-Schrieffer-Hager model, which at that time, when the people start to look at these conductive polymers, what they call conductive means that, for example, acetylene, ethylene was one of these examples, where typically when you have these polymers, they have wide band gap. Okay, and then it has been shown that actually you can make these systems conductive, that when you start to dope them. Okay, and then there are very rich physics behind of this. But to understand simplicity of this model, let's assume now that we have this kind of SSH model, which is the easiest one. And I will try to introduce the concept of topology here, and means what does it mean, concept of topology. So in principle, if you, now I have a system which has like double bond, simple bond, double bond. So my unit cell is like this. I have a two side of energy, two hoppings, and now I can write down the equations for that and I can solve it. So I have just one electron per side. But I'm assuming that one, it will be stronger, the hopping, another one will be weaker. Okay, the T1 and T2 are not equal. And actually, importantly, is also that you see that actually there is a sort of isomerization. I can make the mirror symmetry, so I can change this guy for this guy, and it's exactly the same system, which is the beauty of this polyacetylene here. He has a two degenerated states. I mean, these dimerizations happen here. These two guys, they could not be the same because of this Peierls distortion, this instability. But there are two solutions. Either you start from left, that there will be double bond, simple bond, double bond, simple bond, or simple double, simple double. But when I look in the bulk, actually, and when I make this calculation of the bond structure, so it's homework. You can do it on with a pencil and the paper. You will get this equation, and now if I calculate this band structure, which I see here, so T1 is bigger than T2, and T1 is again in vice versa. So this one would be basically this kind of scheme, and this green one would be opposite. That will be here. This double bond will be here, and simple bond will be here. Now, and of course, when you start to close the band gap, you go through the metallic state. If T1 equals to T2, we know that it's unstable in reality, but in theory, you can do it. So if I start to tune these two systems, I close the band gap. In that moment, the systems start to be metallic. Okay. So if I go like the graduating one is bigger than T2, then I start to be equalize them, and then I turn it back or opposite. I will get again opening the band gap. So that's what the chemists say, that the difference between the simple and double bond, in their terms, the strongest is the shorter one and the weakness is the longer one, means that I'm opening the band gap, and this depends on the difference between these T2 and T1. Now, if you look in the band structure, these two guys, immediately you say there is no difference. They look exactly the same. If I exchange exact value for T2 and T1, you look at the bulk in the band structure that there is no change. The band structure looks exactly the same. Now, so you ask, oh, so why I should care about this? Yeah, but then what you can do is you can analyze this element, this matrix again, and you can write it in this Pauli matrix. So you can have like Hx, which will be just this part. Then you have Hy, will be another part. And here I'll consider that these two outside energies are the same. The only what is different is T1 and T2. And Hz is 0. So now let's plot this system here. And what you see is that how the Hamiltonian in this H epsilon Hx space is changing. And now I see if one T1 and T2 are different. So now you see that if I'm in the position in the origin, now that's what people call in topology winding number. So when I start to turn here, in this case, the winding number is trivial. So basically I'm running on this solution, and you see that actually if I'm as an observer at 0, I will never turn around myself. But then now when I change this T1, T2, now I go to something where if I'm here in the origin, I have to turn myself around the position. So it means that now this winding number is equal to 1. So in principle, from topological point of view, these two things are different. Now again, you can ask, oh, this is still kind of like very abstract. No, what does it mean, this HK, and what it really means? But now let's go to what we will call the dimer case. So dimer case means that one of these guys, this T1 or T2, will be 0. So I will kind of dimerize. And then maybe you will understand in a minute. So now I will deal with a finite system, and I go to this dimerized case. And just, fully dimerized case is now that I have a double bond either here, so it will be the stronger one, and T0, this simple bond, it will be 0. So what you will find here that actually this is perfect. Here, in this case, which was the one which was topologically trivial, I can saturate all the bonds. So they have one electron here, one electron here. They create this double bond, so there is no any extra electron left. But if I go in this direction now, what I find is that actually this guy on the edge, they don't have contact. There is one free electron in, and that's exactly what is telling this diagram. The origin of this, how basically this topologically involved, means that in the finite system I will have either zero edge states or these edge states. Okay, so it means that now we see that in this band structure, which basically we forget about the phase, the Zach phase or Berry phase, now it seems that it's playing a role. Okay, so of course this is known, and again these topological states are a really active field these days, and maybe in some sense are already like buzzwords. But this topological concept is very important because it helps us to understand like quantum Hall effects, these topological insulators. And recently also people shown that these edge states could be found in these graphene nanoribbons. Okay, so also nice beauty of this kind of topologically protected states is that if you have a system which you work in 3D, it's always these localized states, these protected states are one dimension below. So if you talk with 3D materials in these well semi-metals, you will see that you have basically surface states which are topologically protected, which are living in the bandgap. Then in the quantum Hall, basically you have a 1D system. So these are these edge state which is living and providing the explanation of this quantum Hall. In 1D systems, actually you will have zero edge state which appears. Okay, so important thing here is what I would like to show you in a minute is the thing. What is important? The important is that actually when you go from one topological state to other topological states, you have to close the band gap. You have to go through, if you tune in this parameter, in one moment the band gap is reducing and then it's opening again. And other signature of this topological state is that there should be edge states which appears at the edges if we are talking about 1D systems. Okay, so my proposal going back to these polymers is the following. I will take like these different monomers like benzene, anthracene. So these are like units where you are increasing number of benzene rings here. Okay, and if you look in the band gap of the system, you can calculate it. A certain number, what you see that there is a monotonic decrease of this band gap. But now my proposal is, okay, what I'm gonna do is I will connect these guys in between. Okay, so I will use some linkers. I will build the polymer. And now what I want to show is that actually when I'm in this very simple monomer, these small monomers, the system will adopt this kind of configuration. But then if you go further, at one moment the systems start to behave as this. So you will see there will be change in the p-conjugation on the units, and there will be two radical states, two free electrons at the edge, which will be kind of what we call these topological states. And moreover, when I start to tune the size of the system in one moment, because I told you if I go from one topological state to other one, I need to reduce the band gap. And that's basically very interesting property, because now I can design the polymer which will be almost conductive. There is a question if I can reach really conductive polymers, but this means that now I don't need to introduce extra heterogeneous atoms in the polymer, but I can just make these polymers conductive, at least in room temperature, just by designing the polymer to be very close to the topological phase transition. Okay, so is it reality? So first we do some calculations. And you see, this is just the band structure, time-binding band structure for different polymers. So benzene, anthracene, pentacene. And what you see is, again, there is a closing of the band gap, and then you open it again. So it means there should be some phase transition here. And here, this is the results already of DFT calculations for the monomer, no polymer, just these units like benzene, anthracene, pentacene, etc. And this is already the polymer. And this is done with exchange correlation functional B3 lib. Of course, this kind of band gap, it will change accordingly. But you see again here, there would be some transition. We also, okay, the one other thing is if you really want to prove that you are in topological trivial or non-trivial phase, means that you want to calculate the Zach phase, so-called Zach phase, so this Berry phase across the Peierls zone. And again, we see that there is a change in the Zach phase. And importantly, also I can do the calculation for the finite system. And what you will see that for this benzene anthracene polymer, which is seen here, there is no states in the band gap. But for this pentacene, I already start to see states in the band gap. And here I have to admit that this is basically DFT calculation without no spin polarization. But that's just more like instructive. But again, for this pentacene, I will start to see these edges at the band gap. So very localized states, which is appearing in the band gap, but it's localized only on the edges. So here I'm plotting the wave functions polymers, and this is one, this like conduction band, valence band, which is spread out over the whole system. And then in this particular guy, it's localized very at the end. Okay, so that was kind of like, okay, crazy theoretical.
Can I ask a quick question, really quick? So do you have periodic boundary conditions in this, like this green square here? Or it's just one entity, it's isolated?
Sorry, so this one, what is here, this is the band structure for infinite system. And what I'm plotting here, this is the states of the finite system. Okay, so it's terminated here. This one is already the finite system. I show just one part. It's a like system of 15 units, okay?
Okay. Okay.
So maybe it's a little bit confusing, but you will see in a minute. I will show you like this. So it means if you are, we can do bulk calculations, and in bulk you don't know if you're, because you don't know if you are in topologically trivial or non-trivial unless you calculated the Zach phase. Okay. In finite system, you will see if you are in topologically trivial or non-trivial by appearance of this edge state, which in bulk you will not see it because you don't have the terminal system. Yeah, is that clear?
Yes.
Yeah, okay, so let's now go to reality. So we talked to chemists, and the chemists from Spain, they provide us these precursors. So it's like anthracene, there are 2 bonds, and then you have 2 bromines here. And that's very well known reaction on the surface when you put this kind of halogen terminated molecules on the surface, you anneal them on metallic surface, you anneal them. First, what you will see there is this carbon-bromine bond. You will create a radical, and then if you are lucky, actually these radicals, they will interact with each other. And that's what's from the microscope. So you will put this in UHV, we anneal it on the gold, we anneal it, and then you start to see grows these very nice ordered chain, which are 100 nanometers long. And then we use this high resolution imaging, which you see here. So this is the AFM resolution of this chemical resolution of this polymer on the surface. And we can also use this scanning tunneling microscopy to reveal like conduction and valence band. And we can compare with the theory. So this is the calculated image of bands. Valence band, and this is the conduction band. So you see that agreement is pretty okay. We can calculate the band structure. So this means that you have 2 bands which have pretty good dispersion. So it means that also confirms somehow to give us confidence that DFT is not too bad, because using this DFT we are able to reproduce, let's say, some sort of electronic structure of these guys. And now, okay, we predict that this one is topologically trivial, okay? But now you see these guys are very long. So let's have a look at the end if we will see some edge state. So then you take this, you will search for polymers which is finishing at the end, and now you resolve it. So you see there is no defect here, nothing like that. But then when you do daily the spectroscopy, you see this like point spectroscopy, you see there is no any feature at the zero bias. Okay, so it means there is no edge state. And now the next step is, of course, we would like to have same precursor, but in pentacene, which would be already in this topologically non-trivial state. So again, we use the precursor, which is very similar to one, but instead of 3 benzenes, it has 5 rings. Now, again, you can grow it in very same scenario as we did before, very long chains. And then, of course, again, this agreement between experiment and theory is in terms of electronic structure. But importantly now, when we look at this edge state, or at the end of the polymer, which is seen here, the resolved by this chemical resolution, what you will find is that actually at the edge, at the zero bias, you will start to see very localized edge state, which are only living here. Okay, so it means that indeed here we have a strong indication that this guy is changing the topology. Okay, now we are in topologically non-trivial state. But going back, if you remember, I told you this is also somehow related to the change of the p-conjugation. Because what I'm saying here that now, indeed, and again, what I'm showing here is just the theoretical calculations, and we look in the bond length. And if I look to these topologically trivial states, what I see that the bond length of this triple bond is much shorter than in this topologically non-trivial state. So you see that it's not only how you terminate the electronic structure, but it's also reshuffling this simple double bond in some way. And if you look then in this total density calculated by DFT, so this kind of triple bond which is appearing here, you see it has more accumulation of electronic density. Instead, when you elongated the bond, this accumulation, it starts to be more equal. And going back again, in this high resolution imaging, when we are very close, this bending of the CO is caused by Pauli repulsion. So basically you try to penetrate the one orbital to each other, so the CO start to snake because there is strong Pauli repulsion. And this Pauli repulsion is proportional to the local electron density. So it means that in this particular case, there should be much stronger signal in AFM than in this case. And indeed, when we start to look at details of this bond, what you will find indeed here, you see there is much bright spot in AFM, which means that there is more electron density here, okay? So, and this is not found in these two topologically non-trivial states. So you see, this is this line here, and this is the AFM signal. So this triple bond has more repulsion than in this pentacene, and we also see this Byzantine, this similar polymer, has topologically non-trivial states. We can also have a look in bond length, but this is more tricky, and we don't trust too much this because there are some distortions. But there is a strong evidence basically here. What you see actually is this topological transition, which is somehow for condensed matter physicists is kind of like evidence of edge state. In chemistry means that I change the conjugation, okay? So it means that now, I mean, this topological concept, which is mainly adopted by chemists, physicists, it could be also adopted to chemists. And I think it's very interesting point of view because maybe, you know, the people, they try to understand this kind of p-conjugation, what is the origin, what could be behind, etc., etc. Now, there is another hot topic here, and that in the condensed matter physics, which is this quantum phase transition. So what does it mean, the quantum phase transition? Typically, we know a lot about the classical phase transition, but the classical phase transition are driven by temperature. So it means that, you know, example, if I take the water, if I cool down, I will get ice. And now I start to round the temperature, and basically, which means I start to increase the entropy. And then I see subsequent phase transition happening. But these days also people start to look at different kind of transition which happen at zero temperature. And that's what basically there you can start to tune your system by different by different external stimuli. It could be pressure, it could be magnetic field, whatever, but not the temperature. And at zero temperature, at certain critical point, you will go from one phase to other phase. So, for example, I can imagine that I have antiferromagnetic solution, and in one moment when I start to apply the magnetic field, I will get a magnetic solution. Or I can just change the doping of the system. And that's where basically I go from one phase, which could be the phase antiferromagnetic, and I go to some other phase, whatever. But here what happened, and why is this important, okay? So first of all, I mean, this kind of phase transition, again, is related to crossing of two frontiers orbitals. So typically it could be seen that I exchange two orbitals. And I will show you in a minute that topological phase transition exactly the same. You are changing two orbitals. And you can distinguish either it's first order quantum phase transition or second order. If you have so-called level crossing, so these two guys, they don't know each other, or you have what is called avoid level crossing. So you will never close the band gap. So it means also that there is no interaction between these two orbitals. So now you can, theoretically, you can write Hamiltonian in some, let's say, standard form, and plus then you have some G factor, which is extra orbital. Important is that this extra Hamiltonian here is not changing the eigenstates of the system. It's only tuning these eigenstates. The eigenstates, the symmetry remains the same. And then when you go close to this G critical, of course, you can, now you see what happened is that the band gap is vanishing, okay? It should go to zero. And then again, you can build up on top of that all this critical exponent theory and the scaling, etc., etc. Now, why is this quantum phase transition, why is important for us? Why we should care? Because typically it happens in zero temperature. But importantly, when you start to increase the temperature, what happens is that you will go to what is called some above this critical point, you go to something what is called quantum critical region. And this quantum critical region is a special state, which is very difficult to describe, because now what happened that you have a two competing scheme. You also have a thermal fluctuation. So it means now the system can jump from phase 1 to phase 2. And basically it's living in some, let's say, new state. And indeed, all these strange metals and the new materials which has been discovered, which probably are are good candidates for high TC materials, basically it's believed that somehow this high TC, this new generation of high TC could be understood from this quantum criticality. And it looks very, very interesting material properties. Again, the quasi-particle picture is no longer true. And it's mostly related like to very complex interplay between spin, phonons, etc., etc. And typically people go to very, very complex systems. So there is one example like spin waves, then you have some diluted triplons. And what happened here? There are many materials now these days where basically people try to really tune the system to this quantum critical region and study there the properties, and on top later on probably build some theories. And again, I want to go back to this p-conjugation transition. So if I go from one transition to other one, there will be crossing of these two levels. And now just have a look, and I will show you here what happened if I take my pentamer and this pentamer and anthracene. So what you see here is that actually, let's have a look in this band structure calculation, okay? So this is the conduction band, and this is on the edge on gamma and K, and that's what is here, okay? So you see that they have different here, but in principle, if I start to look in this extended state, what happened is actually that this state, which was in valence band, now appears in the conduction bands. And again, if I would have time, I could show you that actually this is something to do with this very phase, because which I start to integrate here, the phase of this guy is different than if I across the Brillouin zone. Okay, so again, there is an internal correlation to this very phase. So now, next step, what I want to show is, okay, I told you that this this pentamer, this pentasync, we had very close band gap. So it means that we are very close to the phase transition. Okay. Now the question is, we have been looking very long chains, and the question is, can I tune somehow my system to really be very, very close to the phase transition, or even better, may I tune the system that I will go through the phase transition? Unfortunately, in our case before, it was not the case, because here you cannot tune the system just adding, fractional benzene rings. It's not possible. So let's have a look to this guy. But now I told you, let's have a look what happened with the length. Okay, so that's what is here. I could go further, but we were meticulously look at the system when we were been looking at different lengths of these polymers, of this pentasync. And now here you see this is measurements over many of these guys, and you see this is the band gap, how it's closing. Okay, so then you see that the band gap where you have a short chain, it's wide, and then it starts to close, and it remains almost constant. But importantly, if we have a critical length of, let's say, 20 units, what we found is actually that now this chain, first of all, he's not featuring any edge state, which is strange, because before I told you that it's topologically trivial. And if I go to one which has just 1 unit more, this one has 24 and it was 25, now these edge states, they appears. Okay, so you see these guys are here. That's image taken and very low bias, please believe me. But what more, now if I look in the valence band and conduction bands of these two chains, now the symmetry exchange. What was before the conduction bands becomes valence band, and what was these conduction bands becomes valence band again. Sorry, so there is an exchange here. Maybe you see that this guy who has a contrast here, it was all empty and now is occupied, and vice versa. And again, if you look in this region, I told you this triple bond, in this long chain, it's not here, but here you will see it. Okay, so you see that basically with length, I can tune again this phase transition. So this is good news. I can say that now I can go through this phase transition just looking at units. So what is behind all this again? And that's what is called this pseudo-Jahn-Teller mechanism. Okay, I will try to explain a little bit what is it. So typically the systems, this molecular system, they don't like to have degenerated states. Some electronic degenerated states, what the system tries to do is to lower the energy and the gain energy with that, in price of some geometrical distortion. Okay, and so typical, and how to understand this is that you have to look in total energies with respect to the some displacement, which are related to some vibrational modes. So typically, if you are in a stable system, what that means that your stiffness, your potential, which you will see here, is actually has one minimum. Okay, but now let's have a look. If I have some displacement, some vibrational stuff, I can have some second order expansion of this potential energy landscape, which will be basically interaction of my wave function with some vibronic effect. So it means derivation of the Hamiltonian with respect some vibrational mode. Okay, and of course there are some selection rules for that, but this guy is basically it may be negative, so it may destabilize the system. Okay, so that's basically off diagonal the terms of this vibronic coupling. And now let's take like two-level system. Okay, so I have two electrons, two levels, and now what I will do is I will introduce this vibronic coupling. So if the vibronic coupling is weak, I have this parabola. So this is the energy. I have two systems when I'm here. So I have two parabolas which goes like this as a function of Q. But now when I start to introduce, and this one is this delta, which is here. But now when I start to introduce this vibronic coupling, in one moment it's too strong. What happened is that there is new minima appearing here. So it means that the system is unstable, it undergoes the transition. Okay, and this actually means this kind of transition has two parameters. Okay, So driving mechanism for this transition from one let's say stable state, when I start to tune on this vibronic coupling, it's as lower as the band gap is. So going just back, sorry, you can derive this one. There are two parts which makes this strong or weak. This. So the first part is basically this vibronic coupling, and second part is difference between HOMO and LUMO. So if the HOMO-LUMO is lower, the vibronic coupling is stronger. It's also the excitation or virtual excitation of some electron gas due to this motion is easier. And so when we look in our graph where we took for different monomers, where we took these band structures, actually what you see here is at the moment here, this is the phase transition when happen. It's about like 25 units. So you see that the band gap is already constant. So there is no, it means that of course this one contributes to this in the vibronic coupling, but in the regime when we observe this this transition, this band gap is already constant. So it's not entirely driven parameter, because typically in all these molecular systems, this is the leading term which makes the stabilization. But then let's have a look in this vibronic coupling. Okay, so this vibronic coupling, what I have to do is some integral of, or the coupling of my wave function plus some vibronic system. So that means how the Hamiltonian is developing or changing with respect to the all vibrations. So this means I have to check all the vibrations, but here what I can advance is that basically there is a most important vibration is this mode. Okay, so it's a strange mode of C of this triple bond, which we see is getting weaker. Okay, and indeed there is a mode which is strongly affecting this bond length. And now how this means how it's changing the Hamiltonian here, it's also related, this vibronic effect is related to the symmetry. So if I have something which is symmetric or antisymmetric, then also my wave function has to be symmetric. So it means this kind of transition from occupied to unoccupied state through this vibration is allowed. This is not zero. And this also, because both are ungerade, so they have the same symmetry, again, this coupled to this one. But if I have two guys here, which they have this occupied and unoccupied, have different symmetry, this vibronic is zero. Okay, so that I can calculate it. I calculate it, and you see here that basically, if I have a transition between two orbitals of the same symmetry for this vibronic for this vibration, there will be some coupling. But if they are different, this will be zero. So now I can do the calculation in DFT, and here what I see is the transition happens at different stage. It happens between 10, 11, which is disagreement with experiment. But of course, we know that DFT is not doing very good job for this kind of excited state. But still, we can capture this this transition in DFT, but it occurs for shorter chains. But now, let's have a look to this effective vibronic coupling, because what you see here is when I make the system larger and larger, what I'm doing is I'm developing some kind of bands here. You know, so for dimer, this is what you've seen here. This is my HOMO-LUMO. I have only 2 species, but if I go for trimer, I already start to have 3 in valence and conduction band, 4, etc. And then when you go growing further and further, then you have more and more states which develops in the band. Now, if I can have a look in this, let's say 5, what you will find is that actually here, if I look to these guys, I will see, and that's what already I've shown you before, when I have this band gap, I go in conduction and valence band, I go to the mixed state. So the state which is in gamma and beta are different. Okay, they have different symmetry. So for example, this guy here always has all these guys here and have a bonding state here. But now I go to LUMO, and actually now I start to see that here there are some bonding states. Okay, so this one. So for example, interaction between this one and this one is 0, but interaction between this one and this one is non-zero. Okay, so there are terms which basically couple to each other, because now this band is made of mixed geometry, gerade and ungerade, and this one is also made of mixed geometry. So it means now I have certain orbitals which couple by Vibronic effect. If both would be of the same symmetry but opposite, there will be no Vibronic coupling. So it means that the system somehow, with these Vibronic couplings, wants to purify this band to keep the same geometry, same symmetry. So now we can calculate it. So we did this calculation for all these many bands. And what you see here, unfortunately, I don't have it here, but you see that now the important is that this total Vibronic coupling, this number of units is increasing. It's increasing because I have also more vibrational states. So there is assumed here over these bands, which contributes, but also about the vibrational modes. So in one moment, what happened is that actually this vibrational mode, this vibrational coupling is getting stronger and stronger. Then basically the system collapses, and these two levels, they exchange, and you will get now this Vibronic effect due to this vibration is zero, because now I have a conduction and valence band which are of the same symmetry but opposite. So it means there is no longer instability here. Okay, so this is the reason what we see now, and you actually can now understand that this Jahn-Teller effect and this kind of like, let's say, symmetry which you have inside of the band is ruling your phase transition. Okay, so it means that now I think this is a nice example that we can also study this quantum phase transition in this p-conjugated system, because these are much simpler in the sense that we don't have to deal with spins, etc., etc. So the systems start to be much, let's say, easy understandable, if you want. But there is one more thing that actually I'm not showing here, but recently we also discovered when you are very close to this phase transition, now when you start to do the simulations, so in temperature, in finite temperature, what you start to see it actually that the system start to jump from one side, from one phase to other phase. So for example, if I have a system which is of 15 units, now I put the temperature so the system can start to relax and vibrate. What you will start to see that the system and start to jump or fluctuate between these two states. And what more, of course, is going through the closing of the band gap. But what more, he's developing new vibrational states which were not observable in this system, which was far away. So it means that in close to this phase transition, what you see is also that there are new vibrational modes which are related to this kind of new states, which is kind of pendulum going from one side to other side. And these states are very coherent. They stay, these vibrational states, they for picoseconds. Okay, so maybe this could be also key to understand, for example, transition or transport in these long polymers like proteins. Okay, because typically they should not be conductive, but at certain moment they may start to be conductive. So it means when you turn these polymers, therefore p-conjugation, very close to the phase transition, you introduce the temperature, maybe they start to fluctuate different p-conjugations, and this makes them very conductive. Okay, so this is first part of my talk. Maybe I don't know if it's not too much. Maybe we can stop here, or if you want, I can also share some results on this, the proton tunneling, etc., etc. But maybe it was too many information already, I guess.
We have more 10 or 15 minutes.
Okay, so if you want, you will get it. Okay, so now let's go to the second topic, which is related to some concerted motion of tunneling, of concerted proton tunneling in one-dimensional chains. Okay, so H-bonds. H-bonds are pretty interesting. I mean, these hydrogen bonds, these guys are responsible for life because, of course, these are those bonds which are scissored every day when we eat and so on, because they don't cost too much energy. So let's imagine if you have a living organism who has to, for surviving, break every day any covalent bond, it would cost so much energy that we would just eat. And that's so the hydrogen bonds, they are kind of weak in the sense, and it means that the system, when he wants to make some protein, etc., that's not too much energy to break. But they are interesting because they are living somewhere in between, and there is a discussion if they are covalently bond, if they are strong bond, and so on. And of course, they surprisingly they also play very important role in mechanical properties, or for example, if you want to understand the phase diagram of ice under high pressure, you have to really involve the reaction where you take in account not only the electrostatic interaction between this positive hydrogen and oxygen, but you already have to take also in account possibility that actually this hydrogen will not jump over the barrier, but will tunnel through because it's hydrogen. And so it means this quantum tunneling of proton is pretty important. And then you can also design different kind of like bonds, hydrogen bonds. So it means when the hydrogen stays in one position, we call them so-called normal bonds, and then you can have lower energy, and then you can have also what they call single well bond. Okay, so it can be shared in between, which doesn't mean that there is a tunneling. It's just that the bond is symmetric somehow. But again, this arrangement of these hydrogen bonds, it may play a very important role, for example, for ferroelectricity. So it may change completely the system from being ferroelectricity to non-ferroelectrics. It has been shown that actually also recently, or a few years ago, that if the electron, if in water, if the hydrogen or proton is jumped to other one, and you have some cluster, sort of cluster, this cannot happen just once. All of them, they have to jump. Yeah? So it means that because then you would have this Coulombic disaster, that you would have the one molecule which would be plus, another one would be minus. So the system in principle doesn't want to do it. And recently, maybe you noticed there is this sulfur hydrogen material, which is very interesting in terms when you put the high pressure on it, it will start to be the high TC superconductor, and you can reach the temperatures of 200 Kelvin, which already is remarkable. And the question is, what really makes this superconductivity behind? And one of the possibility could be that actually when you press it, you go to something where you are very close to it, and then the hydrogen may tunnel through, and maybe it could be behind all this. I don't think that this is the case according to the recent data, but okay. So now let's have a look to this special molecule, which is Kinon molecule, and it was produced by Olivier Siri from Marseille. He's our chemist supporter. And this molecule drew me attention actually, because if you look to this molecule, so it's very simple molecule. It's just a benzene, and here you have a like NH2 and an H on both sides. But now if you look at it, this is one of the few examples when I transfer the hydrogen from one side. So there is a kind of like tautomerization, that this hydrogen can go from one side to other side. But what is interesting on this, if this happens, actually this conjugation or this double bond inside, it has to change. It means that if I have just one nitrogen here, this has to be a double bond, and this will be, of course, the simple bond. But when I transfer the electron, all these guys, they have to reshuffle. Okay, so it means that now if the proton transfers, there is a strong impact on the whole system, on this p-conjugated system, which we thought it's a combination of electrons and vibration. So it's vibronic, real vibronic system. So at the end, there is a question actually, what is the real structure of this? If it's like not, instead to plot it like this, if you should not plot it like 2p delocalized system, which they don't talk to each other. Okay. So that looks interesting. So let's now put the molecule on the surface in low temperature, and that's what we got. Okay, so we put this molecule on the surface, and now we start to see this is the gold. These are not the chains. This is just the herringbone reconstruction of the gold. And what you find is that there's something interesting, that now you see that we have very straight chains. There are some defects here, which we identify later on with this high resolution imaging. We identify them as those which they receive extra hydrogen. Even though we have UHV, so very high vacuum, Still, there is some residual hydrogen, which is very difficult to pump out. So sometimes these molecules, they will get extra hydrogen. And then, of course, because they have extra hydrogen, they don't participate in this game. And now let's have a look in this high resolution imaging. And now this when we take the CO, and this change, they could be up to 100 nanometers. And you see they are perfectly symmetric. Okay, so then you reveal the chemical structure of these guys. What is more interesting is that now we can take a tip and we can move these chains, okay? And that's something remarkable because we say, okay, in principle, you say that these guys, they are connected by hydrogen bonds. But in typical, when you have hydrogen bonds and you come with a tip, you will very easily disrupt the chains or these supramolecular chains. But now, okay, I have to admit it's in 4K, 4 Kelvin, but now we can come up with a tip and we can move it and the chain starts to be very stable. Other thing is that we can deposit also we see also different structures. So when we deposit these molecules, the same molecule, but now we deposit them at little bit elevated temperature. And now what we start to see that instead to be very straight, they start to be like zigzag. There are many defects here. They are no longer straight like this, and they also respect the herringbone. And what is more, when we start to manipulate them, then you see that there is no longer possible to manipulate them. You break them, these guys. So you see, we come with a tip here, we move this guy here, but the original chain remains here, and then basically that's it. So the same molecule deposited in very slightly different conditions, they grow in different way, okay? So what we believe, or what could be explanation here, that of course this, and when we deposit them in a higher temperature, we have more defects, and it means more hydrogenation, and these guys are not unstable. But that's observation. We don't have strong argument for that. But there is one more thing which is behind of difference between these two guys. So, I'm sorry, it's not here. Oh, there's something missing. Sorry. One can say, I will show you a minute later on where we see what the other difference. So now you can ask, okay, here what happened is that maybe what happened is we deposit in room temperature, and now maybe there's some gold atom where are in between, and you create the organometallic chain. So it would be something like that, okay? Or you lose all hydrogens, and now you have something like this. So this could be by the fact that actually the lattice vector of this guy is much shorter than we observed. And the second thing is, okay, the problem is when we consider this gold here, it has very similar lattice distance as those original one. But indeed, sometimes we see this gold, but then the contrast is completely different, the incorporation of gold or some metal atoms. But it's completely different. So that's very rare case, and you see that now these high resolution images is completely different, and you really start to see the gold here, which we do not see here. And other thing is that if you have this gold, it will be more commensurate with the substrate. But here, when we do this high resolution imaging, and we can also image the gold underneath, you see that it's uncommensurable. So it means that we can move also very freely these molecules on the surface. So now the hypothesis is that maybe this proton tunneling is playing a role. And for that, what you have to do is to really get involved these guys, this effect in calculations. Of course, you have to go beyond von Oppenheimer. You have to do what is called path integral molecular dynamics. So now what you treat is that also nuclei, they are somehow presented in quantum way. And how to do it is that actually you create for each atom, you create a replica which you connected by some effective spring constant. So you have this what is called ring polymer. So now each atom is represented by few images, okay? So it's kind of like sampling this wave function with this kind of polymer where you have particles, effective particles, which are connected by these springs, okay? And then this somehow represents your wave function. So this path integrals is actually evolvement of these ring polymers along the time. And of course, this path integral, the engine for that is kind of DFT calculations. This is our home build code, which is then connected with this path integral molecular dynamics, which is extra code. It's a like interface which is running and calling this DFT. So we did these calculations here, and this is the result. So these are this is the barrier when we move a proton from one side to other. So I take the proton and I take it from here to here, and this is the barrier. So this is a classical barrier at 10 Kelvin. It's about 300 millivolts. Now I can do the same, this path integral molecular dynamics. Now here the temperature is very important. And you go down, and now what you see is actually that now this barrier is no longer what we know, this classical Gaussian shape, but it starts to like evolve this dip in between the barriers. So the barrier is dropping, but of course also here is kind of like new minima which you will find, and that's what the people call the d proton signature of d proton tunneling. So it means that proton is no longer on one side or other side, but also he has a certain probability to penetrate inside. So you can see it already here, okay, that the proton already is sampled somewhere in between. And that's indeed in this phase transition, this transition state, you see it's happened here. There is one more thing. It's unfortunately I couldn't show you these guys here, but they are off, okay? They are not exactly symmetric if I look to this. And to explain this symmetricity, I really see that actually this kind of delocalization of the protons makes me the image very symmetric. Okay, so there is another evidence for that. But now what is interesting is actually that now what is the motion? You can ask, okay, when there is only one electron jumping, or there are many electrons. So all, not electrons, but protons, okay? So one proton, and now we can see it in the simulation when we do this simulation. And the simulation, what I plot here is a correlation function of the proton being here, or this proton being here. And now we see that actually when this proton moves here, and this proton has to move silently or correlately also here, because, and then, so it means now what you have here, you can see it as a current of protons running in the circle here, which is concerted motion of the protons, okay? And that's maybe also enhance all the stability of this chain. Sorry, oh, it's here. So I told you like these chains which are unstable. You see that when we do this high resolution imaging, they are not exactly straight as we see those guys. They are flipped a little bit. And when we do the calculation, so this is the DFT calculations made, optimized structure. And then when we calculate this image is perfect match what we have here. And when we introduce this proton tunneling, now you see that everything becomes symmetric. So it means that what we claim here is that actually when you switch on this proton tunneling, so this concert motion, that these protons, they start to jump each, or I mean, it's a naive classical picture, but these protons now behaves as a wave function. And so they move, but in concert way, okay? So now everything is more stable, and then probably you gain some cohesive energy by this concerted motion of protons. But there is one more thing, and when we look at these guys, and these straight chains, there is appearance of edge states or the band gap states inside. Okay, so what you is very straight, very strong peak in zero bias, or very close to the zero. First, we have thinking that maybe it's also related somehow with the topology. Unfortunately, we calculated the Zag phase for this, and we found that actually this should not be related to topology. Okay, but how to explain this guy? Okay, how to explain this origin of this edge state here? So for that, what we did, we calculated the chain. We took this p orbitals in the chain, and now we assume that, of course, normally normally they are very weakly coupled, so there is no electron tunneling through, and this coupling between these unit cells. So this is the matrix of the single molecule. And now what we will do is we will just make the chain time binding model, And we will play with these intramolecular hoppings, okay, which normally in DFT are very low. But now there is a proton transfer here going on. And this proton could be also seen as a, now the question is if when the proton moves, if he's dragging electron with him or not. But in principle, there is a frequency of changing this guy here. So you can effectively see it as this coupling, electronic coupling in the time binding model will get longer and longer, stronger and stronger. And now when you start to play with this, you will start to see that at certain conditions, for some reasonable value like hopping, which is still lower than the hopping inside in the intramolecular hopping, but in the range of 0.3 to 1 eV, you start to see that the edge states start to appear here. Okay, so maybe what we can say is the electronical states here, which appears here, is due to this proton tunneling, which is dragging the electron itself. It's enhancing the effective hopping, electronic hopping between these two units, molecular units, and this gives rise to new electronical states. Okay, so that's it. I hope that the last part I've shown you that these hydrogen bonds are not so innocent in terms when we work in low temperature and when you have a strong coupling with the electronic states of the proper molecule. And of course, this work is not my work, is a work of the whole group. There are many collaborators. So I would like to acknowledge all the people involved in this, of course, also international collaborations. And of course, thank you very much for your attention. And I hope to have some questions.
So fantastic. Dikwi, thank you for this really didactic talk. It's time for questions. If you have any questions, please raise your hand using the reactions here, and we will be glad to unmute your microphone. Who will be the first one? No questions? Cedric?
So Pavel, thank you very much for the very interesting and inspiring presentation. Very dense as well, I must say. You guys have been doing a lot of interesting work there. A few questions come up to my mind, some a little more technical, others a little more general. So let me ask you first, I mean, this path integral molecular dynamics that you have implemented, how does it compare with Ehrenfest dynamics, for example, in terms of computational burden?
Yeah. But I would say these two are a little bit different because like this Ehrenfest is more like about excited states. And here what we really want to treat is these nuclei as a quantum particles. Okay. So of course so it means that like Ehrenfest goes more like go beyond this non-adiabaticity. Okay. Here this fast molecular dynamics is just, you know, that you want to treat this nucleus as a quantum particle. So in principle, this IPI is a package which was developed by other people. And so what you need is actually you need to feed some forces which are acting on your atoms. Okay. So in principle, you don't need electronic structure. What you only can do is just kind of sampling of these ring polymers. So in principle, you can also use time binding, simple time binding. And then you will get electronic structure and so on, and forces acting on. So in principle, there are like two ways. And then you can, of course, use some very expensive DFT or even go for something even more crazy. And that means that in this case, we use our DFT firewall because it's kind of cheap. So again, I mean, that's one. But there is one important thing here. And I think what we are missing here in this calculation, and that's because you could ask, okay, now you go to DFT or you go to this path integral molecular dynamics, and maybe you should see this edge state. You should see somehow this enhancement of the bonding. But unfortunately, this is not the case because this IPi is one part, and the DFT is always DFT, is nothing else in between. And I think to really capture the idea here, or what is happening, is to implement what you asked for, include also this end first, or some non-evatic dynamics, because actually what you are doing here, this proton, is strongly coupled to all vibronic effects. So basically, again, you are changing two wave functions in between each other. So there is very strong electron-phonon coupling, and I think no one can do it now. So what we now trying also to understand is that you can take it from different perspective. You can take this time-binding model, which we used, but so far we have been using only real hoppings, but you can also go for imaginary hoppings, which you have. And then now the question is what they means. Okay, you can have you can imagine that these imaginary hoppings are kind of related to lifetime or some more sophisticated interaction with in terms of quasi-particles. So that's one of the things we would like to check. Yeah. But that's again simple and that's very open question and very interesting. And honestly, that's just, we feel there is something there, but it's difficult to capture it now with these days. Actually, I can say that we had this paper in Nature, and it was rejected because I think by a referee, because he didn't understand what we are talking. He was asking us to calculate some rates, but the rates for this concerted motion, no one can do it, and that's the problem. We can estimate some rates, but these rates, it's exponential, so you can get whatever you want. I mean, it's not.
Okay, another question, a quick question, Pavel. You were talking about this molecular system or polymers that are infinite, but I was wondering, for example, it seems that Peierls distortion is an important ingredient in this quantum criticality of yours. So it came to my mind, the crystal structure of tellurium. I don't know if you're familiar with it, but it is basically these unidimensional chains which are Peierls distorted, and the chains connected with each other through van der Waals interactions.
Yeah.
Do you think that, but it's a 3D structure, right? So do you think you could observe something like that if you took the longitudinal direction for carriers propagating in tellurium, for example, even though it is three-dimensional?
No, I think you are perfectly right, because if we thought, I mean, oops, I'm not supposed to. So, for example, I mean, this is, all the systems big people now deal with, this magnetic system, with this superconductivity, whatever. They talk about, I mean, it's very difficult, because what they do is they play with with Hamiltonians, like some modeling Hamiltonians, and they are looking at the spin state, okay? But I think what is the very important part of this story is again this Young-Teller distortion or Peierls. So it means if I create this kind of pairs, it's not only that they are electronically coupled, there will be also relaxation of the positions. Now you can ask what is first, if it's chicken or egg. What is the driving force? Is it this Vibronic coupling, or is it really like magnetic interaction which is driving one or the other? I mean, that's why we think that it's interesting to look at these polymers, because there you make it much simpler. There is no spin degree of freedom. There is only, let's say, this driving force. But I think the lesson here is that, I mean, the people working in this field, they do a great job, but they don't look too much at this Young-Teller distortion. They just look at, let's say, all these correlations based on the spins, etc., etc. But in principle, I think maybe the key to understand all these things, or not key, but very important ingredient is this kind of lattice distortions, which are there, definitely.
Okay, ďakujeme moc krát, Pavel, a gratulujeme za hezkou prezentaci. Díky.
Thank you.
I guess it's thank you.
João. Gracias.
Gracias. João, it's your turn.
Hi, Pavel. Thanks for the very nice talk. I also have a question about this quantum phase transition topic. Did you try to observe what's happening at the quantum critical region? So for non-zero temperature above
this we try by DFT, which you say is very nice, and I told you about that we start to see this kind of oscillations, and you are pretty right that it will be great to see if there is any fluctuation also with the temperature, but there are experimental problems. Okay, so the first problem is that of course all this imaging can be done only in very low temperature. So raising the temperature in our microscope, this is designed, let's say, for temperature of 5 Kelvin or 1 Kelvin. If you go a little bit further, we can heat up a little bit the system, but then the problem is that you increase enormously the drift, so that everything start to move. So it will be very difficult to get such nice images. There is another issue, is that when we do this kind of imaging, the image takes about 10 minutes. If you really want to get such kind of image, scanning probe microscopy is terribly bad in time resolution. But these days, people start to combine STM with terahertz. And there you can increase actually the time resolution. So it will be kind of spectroscopic resolution, Then you can increase the spectroscopic resolution or time resolution to this femtoseconds. And that's actually what we want to, that's one of the things which probably would like to explore now, to really tune to close to the quantum criticality, and then try to, for example, see this terahertz spectroscopy, if you will see some signature of fluctuation. So the scanning microscopy is moving in this direction, but it's really like on the edge. Yeah, but it will be extremely interesting. Other possibility how to overcome this problem maybe is to lift up the system. So that's we do for other system, not yet for this one, but let's say lift it up there probably, or start to completely different kind of measurement where you can increase the temperature and look at the transport through this virus. Okay, because then you should start to see these effects, and that's also something which we are aiming, but of course it's not easy. Yeah, but you are completely right. It will be extremely interesting to start to look at it, but it's it's also fresh because we didn't expect this kind of behavior that you can tune it by length, and also we are learning already. So that probably is also something which we are thinking now how to continue with this and prove this kind of coherent oscillations and all these things.
Okay, thanks. Just another quick question. Is there any signature on the size of these chains? Do they, like, the size of the chains change anything on the physics, or it's only the monomer size?
Sorry, what do you mean, like this edge state? Or
so you have a few monomers, right? You consider a chain of like 20 monomers, the physics is more or less the same of a chain of 200 monomers, or?
Well, it's a very good question. It's actually, if you look to this system, you can claim these are not strictly edge state, okay? Because they are not localized here. They are localized more inside. So, and then indeed, when you look at these guys, unfortunately, I don't have the slide here, but it seems like that the p-conjugation on this guy and this guy is preserved somehow. So that's not completely turnover of the whole p-conjugation. So it seems like at the edges, this guy still wants to be more like triple bond, and then it push the edge close, like not exactly at the edge. And now we have other, I don't have it here, but what we can do is also, we can hydrogenize these very long chains, and we can start to dehydrogenize them. And then you will create like boxes of these guys. And you can play also, like you have two boxes close to each other, which are topologically trivial, non-trivial. And then some of these edges, sometimes they disappear. So I think there is still something behind, all these things, how they behave. And again, it's very tricky. So I think that and you know, you should look at this as a snapshot of low temperature. Maybe what may happen is, if we will be in real temperature, or some elevated temperature, so maybe these guys, they will start to travel. So you could call them like solitons, maybe, but then we don't know. We can't observe it. So probably you need to design some other microscope for, let's say, this. But in principle, yes, they are not equal. You know, it means that also there is a variation. Also, we see it in DFT that actually these.
We lost him. Okay. Just a minute. We lost the connection.
Sorry.
Okay.
I'm back.
Okay.
Yeah. Sorry. I mean, so I hope that I answer your question somehow.
Yeah, sure. Thanks.
Yeah, thank you.
Carlos, please. Carlos.
Yeah, thanks for the presentation. It was very nice. Yeah, I have a short question about the diagram you present for topological transition from trivial to non-trivial in polymers and monomers. So you showed in a very nice way how we have this topological transition in polymers, and it's a very nice plot. So are you implying with the line for monomers that we also have a topological transition without close the band gap in that case?
So you mean this one?
Yeah, exactly. So I am very curious because for monomers we have this red line. However, we don't have any signature of a kind of, you know, inversion of states as you present for polymers. So I'm curious if in this case we can have this kind of topological transitions without close event gap.
Okay, so good. Yeah, I mean that's kind of like, you know, let's imagine that I will start this benzene. I will take like two phenanthrene, this pentacene, and if I will just grow it, you know, this is called of acenes. In one moment, you will again, so that's different kind of polymer, you know, that will be polymer made of these benzenes. So in one moment, again, and people know, chemists, they know that they starts to be biradical. So it means that again, they will start to develop the state at the edges here. And there will be again like close of the band gap. If you do it just in DFT, you will find that at certain way you start to develop the band, and there will be also some crossover. Now, the thing is that I think also there's been done some DMRG calculation with this many-body, because this is perfect for these one-dimensional systems. And there again, maybe you will see something like this topological phase transition, if you want to call it topological phase transition. I didn't go too much in details here, but still, you know, because then also we can start to talk about the Zag phase, how to define it, what is the unit cell. I mean, but you are right. If I do this kind of like polymer, which is made only of benzene, in one moment, I didn't plot it here, in one moment, again, you will close the band gap and open it. The question is, that was observed in DFT, and I'm not sure if this is really true. The people still, they speculate about it, because probably you will need some this quantum chemistry technique or technique which goes beyond single determinant to really answer this question. But in principle, in one moment, you again have this system turns to be from aromatic to kinoid, and you will have a 2 ampere electrons. Now the question is if this is really topological, trivial or non-trivial.
Okay, just to be sure, do you compute the Zag phase for this kinoid, by the way? Just to verify if you have a kind of, at least in the DFT
for this
framework
one
you use. Yes.
Yeah. This we did.
Okay.
And actually the change in kinoid is is related to this change of the phase of the exchange of these orbitals. You know what you see
Yeah, but
here.
this is the polymer, right? Not the monomer.
For monomer we didn't. I mean, but I
Okay, I
mean
got it.
there are few studies. Yeah, but then the point is that the Zag phase you can calculate it only for infinite system. But I never try. Okay, I don't know.
Okay, okay.
Yeah.
Bueno, muchas gracias.
Yeah, de nada.
So, okay, like we don't have much more time. Thank you, Pavel, for this really nice talk. Enesio is going to Praga to work with Pavel. So Enesio is here. Is Enesio here?
Yes, I'm here.
Okay, you can give us some words because Enesio, part of our program, is going to work with Pavel. So congratulations, Enesio.
Thank you very much.
Yeah. Okay, great. So I'm looking forward to, guys, and maybe we can start some collaboration. Let's see. Everyone is welcome to come Prague, of course. But now these days, you know, it's I got today my haircut, so it's kind of, you know, luxury these days because everything is closing.
Yeah. It is a luxury I haven't had in a while, Pavel, as you can see. But it's interesting because after Enesio spoke to you and he got the offer, I learned that Martin is also hiring a Brazilian postdoc from Unicamp.
Yeah. He's hiring another Brazilian postdoc. So there will be, you know, there will be strong
So I mean,
growing. Yeah.
Exactly. And I didn't mention to everyone here, but Martin was in Brazil as well when I met Pavel. And after he went back to Europe, he started importing Guaraná in powder.
Yeah.
So I bought Guaraná sometimes for him at the Mercadão and sent it to Prague, you know, and he said that it was just selling so much in Prague. All the scientists were addicted to Guaraná, and I think that the ground is already laid there for a Brazilian community. Next thing is going to be pão de queijo.
Actually, Martin now he's independent and he established his own group and he's doing fantastic jobs on single molecules and photoluminescence. So if you guys can invite him, I think he's doing really amazing jobs. So,
well, wonderful. Yeah. I mean,
good. Yeah. So hope to see you in Prague next summer. Let's see.
Yeah. I hope as well, Pavel. Let's see how it goes. You know, it's.
Yeah. Okay, guys, stay healthy.
Thank you very much.
Thank you very much. I hope to see you soon. Bye.
Thank you very much.